Now let's just move on further and talk about the other concept, which is nothing but called as the triangles on the same base and between the same parallels. So first of all, we have discussed about the parallelograms being on the same base and in between the same parallels. Then we have concluded a relationship in between their areas, that they are equal in areas. In the similar base, we are now just talking about the triangles on the same base and between the same parallels. So let us suppose if I'm just having these two triangles, so you can see over here that these two triangles are actually on the same base, that is BC, and in between the same parallels, which is AP, which is nothing but parallel to BC. Now if I just wanted to find out a relationship in between the areas of these two triangles, so first of all, let us suppose if I'm just plotting it on the graph paper on the same way like I have plotted the parallelograms on the same base and same parallels, then I can able to find out the areas of these two triangles by just counting the number of the squares that are enclosed by these two figures altogether. So what can we conclude about their areas at the end? So at the end we can conclude that their areas are actually is equal to each other. So hence at the end we can conclude that the triangles that are on the same base and between the same parallels, they are equal in areas. Yes, they are equal in areas, which lead us toward the coming theorem, which is nothing but called as a theorem in which we have to prove that the two triangles on the same base or equal bases and same parallels, they are equal in area. So let's just prove this particular fact. So first of all, let us suppose if I'm just taking the two triangles over here, let us suppose I do have a triangle which is nothing but ABCD. Let us suppose this is my very first triangle, which is nothing but ABC. Let us suppose if I'm just taking another triangle over here and I'm calling it as nothing but DAC, and such that they are lying on the same straight line. Let us suppose if I'm calling it as nothing but D. So as you can see, we have the two triangles over here. So let us suppose if I'm just starting with the given conditions, that what are given: a triangle ABC and triangle DBC on the same base and in between the same parallels. Now what we have to prove over here, we have to prove that the area of the triangle ABC is actually is equal to the area of the triangle DBC. So this is the thing that we have to prove over here. But before that, let us suppose I'm just doing a little bit of construction over here. So what is the construction that I'm taking over here? First of all, I'm just drawing a particular line which is parallel to BA, which is parallel to this BA or AB. So let us suppose if I'm just taking this particular line which is parallel to AB and I'm calling it as nothing but EC, and furthermore I'm just taking another particular line which is parallel to BD, So let us suppose I'm drawing another line which is parallel to BD or DB and I'm calling it as nothing but F. So the construction would be like draw EC parallel to AB and FC parallel to DB such that AECB is a parallelogram, and along with DFCB is also a parallelogram. So with these two lines, we have actually formed the two parallelograms over here. So let's just start the proof of this particular theorem. First of all, since by construction we know that by construction we have two parallelograms. Lying on the same base on the same base BC and same parallels, then their areas will be equal. By the theorem, we know that if we have such a condition, if we have their areas will be equal, by theorem we know that if we have the two parallelograms that are lying on the same base between the same parallel, then their area should be equal to each other. So it implies that the area of AECB is nothing but is equal to the area of DFCB by the theorem. We know this thing by the theorem. Let us suppose if I'm just calling it as nothing but 1. Furthermore, if I am just talking about this parallelogram, if I'm just talking about this particular parallelogram, then what can we say about the triangle ABC? So again, it implies that the area of the triangle ABC is nothing but is equal to half of the area of AECB, because we know that a triangle and a parallelogram, a triangle and a parallelogram, if lie on the same base and between the same parallels, then the area of the triangle is half of the area of parallelogram. We already know about this particular concept. So using that theorem, I'm just writing it over here that the area of the triangle ABC is actually nothing but half of the area of AECB. Let us suppose if I'm calling it as equation number 2. Now furthermore, again using similar concept, means similarly we can also say that in this particular parallelogram, if I am talking about in this particular parallelogram, which is nothing but DFCB, we have similarly the area of the triangle DBC as nothing but a half of the area of AECB. Using the above explanation again, we can say this particular fact that these are actually is equal to half of this. Let us suppose if I am calling it as nothing but third, this is nothing but is equal to AECB, or rather than AECB, I can just write it over here as nothing but DFCB. Actually, I just have taken this as a direct step, but before that, you can also take the step as nothing but. Let us suppose if I'm just writing it over here that Similarly, we can say that the area of the triangle DBC is nothing but half of the area of DFCB, and this would be nothing but the explanation. This would be nothing but the explanation of this one, because we know that DBC and DFCB is actually lying on the same base and between the same parallels. And again, further, we can say that area of DBC should be is equal to the half of the area of AECB. Why we are calling this as nothing but AECB? Because we already know from the very first equation that this is equal to this. So let us suppose if I'm taking it as from equation number 1, we know that the area of AECB is actually is equal to the area of DFCB. Now, if I'm just talking about the equation number 2 and the equation number 3, it implies from equation number 2 and 3, we can see that the area of triangle ABC was equal to the half of the area of AECB, which is exactly same as that of half of the area of DFCB, which is nothing but is equal to the area of the triangle DBC. So at the end, what we are getting? We are getting the area of the triangle ABC as nothing but but is equal to the area of the triangle DBC. And this is exactly that we have to prove. We wanted to prove that their areas are actually is equal to each other. So hence this is nothing but the proof of this particular theorem. So hence at the end what we can say that whenever we have the two triangles on the same base and between the same parallels, they are always equal in area. Now let us suppose if I'm just talking about the area of the triangle that we are getting from the figure. So for an instance, if I'm just driving or I am just taking out the area of the particular triangle which is in the parallelogram as nothing but, let us suppose if I'm just taking a particular parallelogram over here, and I am calling this parallelogram as nothing but A, B, C and D. So let us suppose this is my parallelogram which is A, B, C, D, and let us suppose if I'm just taking a diagonal of the parallelogram which is nothing but AC. So since A, B, C, D is a parallelogram, it is a parallelogram, and AC being a diagonal, divides it into two equal triangles or two congruent triangles. So if I'm just talking about their areas, let us suppose if I'm just doing a little bit of construction over here, and I am just taking this particular point as nothing but AN, means this is a perpendicular AN. So we can say that the triangle ADC is actually congruent to the triangle. It is a CBA. From this particular fact, it divides it into two equal triangles, which implies their area should be congruent. They are congruent to each other, and if they are congruent to each other, it implies that their areas are also equal. Areas of ADC is nothing but is equal to the area of the triangle CBA, because of the fact that we know that the congruent triangles are equal in area. They are equal in area. So using this concept, we can say that their areas are actually is equal to each other. If their areas are equal to each other, then we can say that the area of the triangle ADC should be nothing but is equal to the half of the area of the parallelogram, which is ABCD, because we know that the two triangles that are lying we have over here, that let us suppose if I'm just talking about this one only, if we have this particular triangle which is lying on the same base and in between the same parallel lines, means we have this triangle and we have this parallelogram, they are lying on the same base between the same parallel line. It implies that the area of the triangle should always be the half of the area of the parallelogram. So we can say this fact by the theorem or by the example, because we have done it as an example. So we can say by theorem we know that the area of the triangle should always be the half of the area of the parallelogram. So using this concept, we can say this is nothing but is equal to this. And furthermore, we know that area of the triangle ADC can be written as half into area of parallelogram. We know that the area of parallelogram is nothing but base into height. So base, let us suppose if I'm just taking a base over here as nothing but DC. So my base over here is nothing but DC and height is nothing but AN, because the corresponding height with respect to the base is nothing but AN. So hence it implies that I can just write it as nothing but half into DC into AN. I can write this area of the triangle as nothing but half into DC into AN, which can also be written as half into base into height. This is my base, this was my base, and this was nothing but the height or the altitude with respect to the parallelogram. So hence from this particular fact, what can we say? We can say that the area of ADC triangle was actually nothing but is equal to half into base DC into AN. So area of triangle is actually half of the product of its base and the corresponding altitude. Furthermore, we can say that the two triangles with the same base and equal areas will have equal corresponding altitudes. They would definitely have the equal corresponding altitude. So this is nothing but all about the triangles that are on the same base and between the same parallels.